Okay, this is Physics 2211, Lab 4, Oscillations. The purpose of this lab was to model the movement and oscillations of a spring and compare it to our experimental data. The fundamental physics principles are Hooke's law, which is the spring force equals negative kx, the energy principle, which says that the total energy is the potential energy plus the kinetic energy, and then Newton's second law, which is the sum of the forces equals the mass times acceleration, and also the change in momentum over the change in time is equal to the sum of forces. Brief preview results. Our model looks similar to our experimental data, but it's slightly off, which is to be expected when we're modeling real-world situations because we can't tell for sure every single force is acting on the system. Our system is the mass that is hanging from the spring. The surroundings are the spring, gravity from Earth, and anything else that exerts force on the mass. The initial conditions, the ball is at rest and then released, and the spring is stretched slightly to create that force. Main physics ideas are Hooke's law, which I already stated, the velocity and position updates, which are derived from Newton's second law, and then kinetic, gravitational potential, and spring potential energy, which the equations are listed on the left. And then on the right, I drew a little free body diagram. This is not the exact free body diagram for the whole entire video because the spring force will always point to where the spring is anchored, not directly up. But gravity will always point down towards the center of Earth. Here is my tracker video. As you can see, the mass moves in sort of an elliptical path, and my data is on the left. And here is my code. The ball's mass, the spring constant, and the relaxed length of the spring were all given to us in a previous video. In lines 51 and 52, the ball position and velocity were given by tracker. Also 105, the time was given by the tracker. Lines 88, 89, and 90 are calculations for the spring, the length of the spring, L hat, and S. And then 93, 94, 95, and 96 are calculations for kinetic energy, gravitational potential energy, spring potential energy, and then the total energy, which is just the sum of all the different kinds of energy. Lines 114 and 117 are the calculations of the spring force and gravity, our two forces acting on the mass. And then 120 is the net force, so we're just adding those forces. 123 and 124 are the position and velocity update formulas. And then the rest of the highlighted lines are just updating the spring and the energy using the same exact equations that we used in lines 88 through 96 initially. Here are my output graphs. As you can see, the position versus time graphs are the same kind of trajectory, just slightly off from each other. And then the energy graph looks to be about right, as the delta E is 0 for this entire interval, meaning that the energy principle is satisfied in this scenario. Similarities and differences. So the experimental data seems to go a bit faster than the computational model, but they both follow the same trajectory, kind of like the same amplitude and stuff. The energy graph seems to be a true representation of the energy in the system. Possible sources of error. There might be discrepancies in placing the center of mass in tracker. The ball might have not started completely from rest when I started tracking it, and there might have been unknown forces acting on the ball, like air resistance, that might have affected its position. What does it mean? For your model system, is the energy principle satisfied? So I mentioned previously it is, because the gravitational potential energy and the spring potential have an inverse relationship, which makes the change in total energy in our output graph 0 for the whole entire period, which was the orange line on our energy graph. And then the estimates of the oscillation periods. Using X data, I got 1.852 seconds. So to calculate this, I used the tracker graphs and calculated the time for a few different periods and then divided by the total amount of periods I calculated the time for. And then using this same method And with the Y data, I got a period of 1.591 seconds. So the difference in this period could be due to a non-uniform spring constant that made some parts of the spring stretch further than other parts, and then it would stretch the X and Y directions differently, which would make the periods of oscillation a bit different for the X versus the Y direction. Okay, thank you for watching. Bye.